Hello AP Stats class, this is Mr. Liao, and we're going to go over 10.3 and the beginning of 10.4 using this video because of the CASI test. That way you can work on problems in class. If you have not seen the video and you want to watch it in class, well, I guess you wouldn't be listening to this, but that's up to whoever your substitute teacher is to let you do that. Feel free to help each other. Here we go. Our goals are twofold today. Distinguish between statistical significance and practical significance, and identify the advantages and disadvantages of using p-value rather than a fixed level of significance. There are two parts of these notes. These are the first two goals out of the 5. So, the big idea for the first section is, while the calculations of a significance test are fairly simple, knowing how to use tests wisely is not as clear-cut, because sometimes the math is easy, but how you interpret, how to use the data is not so simple. So, how small of a p-value do you really need? There are two possible circumstances you'll want to consider. First, how plausible is the null? Strong evidence will be needed to persuade long and widely held beliefs. If you imagine Copernicus or Galileo trying to change the church's idea that the Earth was at the center of the universe, you probably needed a pretty plausible null to get that. So you needed really strong evidence to change that. Secondly, what are the consequences of rejecting the null? Even if it makes statistical sense, does it make practical sense? A lot of times the differences will be so small that it's really not necessarily worth it to implement changes. And we'll see some examples of that coming up. There is no sharp border between statistically significant and statistically insignificant. All we can say for sure is that the evidence is stronger for significance as the p-value decreases. For example, if alpha is 0.05, there's very little practical difference between p-values of 0.049 and 0.051, even though one value will lead you to a conclusion of statistical significance. So remember, in terms of degrees, there's not much difference between 0.049 and 0.051, but one's going to give you a result that you might be looking for, and one will not. So you got to just look at the numbers themselves. Obviously, if you get a p-value of 0.001 against an alpha of 0.05, that's a pretty strong case for rejecting the null. So, even if you find evidence that a change has occurred, the effect itself may be pretty small. Now here's the formula for the z-score, and I've rearranged this one over here, so I put the radical n in the numerator. So what that tells you is that as n gets larger, your z-score gets larger. So when n is large, even small deviations from mu naught will be significant. Now, this thing is not going to change. Well, it will change, but if this is equal, the larger your sample size, the larger your z-score. So you have to be very careful, because even if you have a very small and practically insignificant difference between your sample and the null, the large sample size might return a statistically significant result, even though it doesn't practically make a large difference. So you just have to really be careful, and this is what makes social science and stats so interesting and interwoven, because you have to sometimes make decisions. You have to judge things based on practical reasons, not merely on mathematical. I know some of you don't like that, because some of you want black and white answers. Unfortunately, in stats, there are rarely black and white answers. Let's take a look at example 10.18. Your company has developed a new antibacterial cream. From previous research, you know that with no medication, a small cut on the inner forearm will heal on average in 7.6 days with a standard deviation of 1.4 days. You want to test this new cream at the 5% significance level. We cut, and you can question the ethics of this experiment, we cut 25 volunteer college students and apply the cream to the wounds. The mean healing time for them was 7.1 days. Assume sigma is 1.4. Alright, let's craft our hypotheses. So, we want to know the mean time to heal the cut for college students. So, our null hypothesis would mean no change. In other words, it would still take 7.6 days for this wound to heal with the cream. Our alternative is that the cream improves healing rate or reduces healing time. So we want our alternative to be less than 7.6 days. Alright, let's check our conditions. Simple random sample. Well, we have a voluntary response sample, so we cannot generalize the conclusion to the population of all college students. If anything, we're limited to college students at this college. Normality. 25 is not a large enough number to use CLT. So we're going to have to either assume the population is approximately normally distributed, or we're going to have to proceed with caution. And again, as a piece of advice, if you get a question that's not necessarily asking specifically about conditions, make some assumptions or state you're going to proceed with caution and continue to solve the problem. Finally, we have independence. Each student's healing time is independent from the others. So, independence doesn't always mean 10 times the amount of the sample in the population. In this case, my healing rate is going to be different than yours. Alright, let's take a look at some calculations. These are pretty simple at this point. You get a z-value of negative 1.79 with a p of 0.0371. The calculator screen caps are below. And so, since our p-value is less than the alpha level of 0.05, we're going to reject the null hypothesis. Now, when we interpret this data, only 3.7% of the time would we get a sample mean of 7.1 days if the true mean were 7.6 days. Since 0.037 is less than alpha equals 0.05, we reject the null and conclude that there is a decrease in healing time due to the cream. But practically speaking, what can we draw? A half-day improvement is not practically important. It doesn't really matter if your wound heals half a day faster. It's not like you put the cream on and it heals right away. So just because there's statistical significance does not necessarily mean there's practical importance. And that's one of the caveats when you do statistical significance testing, is that just because you get a statistically significant result doesn't mean it's going to be very meaningful in the real world. So sometimes you're going to have to make a judgment call. Let's go over some other caveats. Statistical significance is not the same as practical importance. So remember, don't suspend your life living in the real world when you do some of these problems. A half a day improvement is not a big deal when it comes to healing a flesh wound. Next, always plot your data. This is something I've harped on since day one. Look for outliers because they can drastically alter results. Next, examine confidence intervals since they provide estimates without looking only at the probability. A small difference may not be practically important. So if your null value is just outside the confidence interval and you're doing a confidence interval significant test, that might not be practically important, though it may be statistically significant. Even with a 5% significance level, we expect 1 in 20 tests to be significant just by chance. Keep in mind, with a 5% significance level, even if null is true, you're going to get 5% of tests that are going to show that you should reject the null even if you shouldn't. And if you run, for example, 20 tests at the same time, probability-wise, you're likely to get at least one where you're going to find the data statistically significant, so be careful. Make sure conditions are met and beware of faulty data collection. Otherwise, you may get invalid results. Garbage in, garbage out. If you take your sample from a voluntary response or you have some other sort of bias, it's going to impact the quality of your data. So be very careful. And if you have bad data collection methods, make sure you state that in your response. Watch out for the so-called Hawthorne effect. This is the effect where if people know they're being watched and studied, they're going to tend to behave differently in the short term. This happens a lot. So the best way to test participants is to tell them you're testing something, but when you're really testing something else. Do not generalize beyond the population of interest. For the cutting of the flesh for the antibacterial cream test, our population of interest there is just college students. Probably college students just of the college that we did our volunteer sample in. Okay, let's move on to 10.4. 10.4. Using inference to make decisions, type 1 and type 2 errors. So our goals this section are to define and describe using a real situation what is meant by both a type 1 and type 2 error. We'll explain the relationship between a significance level and type 1 error on the next set of notes. So, it all comes down to decision making. Because we have a fixed alpha level, we have to reject the null if the p-value is less than alpha. The mere fact that we select alpha in advance suggests that we're going to make a decision on the outcome. However, because statistics is not perfect, we're sometimes going to make erroneous decisions and bad judgments. But our job as frequentists is to try to get it right most of the time as much as we can. So we have these two types of errors. They have been cleverly named and confusingly named type 1 errors and type 2 errors. If we reject the null when the null is actually true, we have committed a type 1 error. So let me repeat that. If you reject the null when the null is true, you've committed a type 1 error. If you fail to reject the null when the null is actually false, you've committed a type 2 error. So I'll repeat that as well. If you fail to reject the null when the null is actually false, you've committed a type 2 error. So basically, there is no great way to memorize this except just remember it. Now, there have been some graphic ways to represent this, and we'll show you those in a few slides. When describing type 1 and type 2 errors, state two things. First, the description of the error in context. What does it mean when you have a type 1 or type 2 error? When you fail to reject the null when you shouldn't have, or when you reject the null when you shouldn't have. Secondly, state the consequences of the action. Use the context of the problem and state what real-life consequences may result if type 1 or type 2 errors are made. So there are basically four outcomes. We can reject the null when the null is true. That's what we call a type 1 error. In other words, you reject the null when the null is actually true. If you reject the null when the alternative hypothesis is true, you've made the correct decision. If you fail to reject the null when the null is true, you have made the correct decision again. However, if you fail to reject the null when the alternative is true, then you've committed a type 2 error. So these are the four possible outcomes, and if it helps you, you can recreate this chart every time it comes up on a test or a quiz. I don't know if there's a mnemonic that I really like that helps you memorize it, but if you can think of one, let me know. Here's another way to represent it. In the first row, I have the null, and in the columns, I have type 1 and type 2 error. And even though this has an alternative hypothesis and the probability, which we'll get to probably in the next set of notes, we're going to focus on the null because it's all about how you treat the null. If you reject the null when the null is true, you've committed a type 1 error. If you fail to reject the null when the null is false, you've committed a type 2 error. The alternative hypothesis listed here is basically the consequence if you commit whichever error up here. The probability of the type 1 error happening is at alpha, which represents the significance level. We'll talk about that a little later. And the type 2 error probability, you won't actually have to calculate this. You just have to know what it conceptually means. You don't really need to actually do the math. The book actually has math problems. The AP test does not require you compute type 2 error probability. So, again, the null. Type 1 error means reject the null when it's true. Type 2 error means to fail to reject the null when the null is actually false. Which error is worse? Kind of depends on the circumstances. Each situation requires its own analysis and interpretation. Some might have better outcomes than others, some might not, and a lot of it depends on which side you're on. So use your common sense, use your life experience, state facts that support both sides or arguments for both sides, and draw your conclusions. Let's take a look at some real-life scenarios of how type 1 and type 2 errors work. First, let's consider the criminal trial, the criminal justice system. Here, our null hypothesis is that the accused, the defendant, is innocent, and the alternative is that he's guilty. So, as a prosecutor, you are looking to find evidence against the null, against innocence, in order to win a conviction. If you commit a type 1 error, you are failing to reject innocence when the guy actually is innocent. Rejecting the null, rejecting innocence when innocence is true. You convict an innocent person. Obviously, the consequences there is that someone that didn't do the crime is in jail, perhaps unjustifiably. Also, you actually do not capture the actual perpetrator of the crime. So there are a couple of consequences there. Type 2 error is to let a guilty person go free. You fail to reject innocence when he actually was guilty. So, you let a guilty person go free. So obviously the consequences there are you have a criminal that's on the loose. So there are real-life consequences of type 1, type 2 errors. And they are going to happen in statistical inference. You just have to know what the possible consequences are if they do occur. Let's take another scenario. Let's call the hypothesis HIV negative, whether you're tested HIV negative or positive. Let's call the null HIV negative. So that's no change. The alternative hypothesis is that you're or someone is HIV positive. So a type 1 error is a false positive. You test positive for HIV even though you are actually negative. So you reject HIV negative when you actually are negative. Let's call this a false positive. And for type 1 errors, you will often see them called false positives. A type 2 error is a false negative. False negative means you actually are HIV positive when you're actually tested negative. So you fail to reject the null. You fail to reject HIV negative when you're actually HIV positive. Obviously, the consequences are slightly more serious for a type 2 error because you could be going around the world thinking that you're clean and you could potentially infect other people with HIV. What actually happens in real life, they will tend to use a cheap economic test for HIV testing that does return a lot of false positives. And if you do get tested positive, they'll do a more expensive test to get a better result. So that's how the 4 outcomes work with type 1, type 2 errors in a situation where you're being tested for the positivity of a virus. Look at a couple of examples on how type 1 and type 2 errors apply to different situations. A potato chip producer and a supplier of potatoes agreed that each shipment of potatoes must have no more than 8% of potatoes with blemishes. Otherwise, the shipment will be rejected and the supplier must provide a new shipment of potatoes. The producer inspects a sample of potatoes and uses a significance test to decide whether to accept or reject the shipment. So, our hypotheses, if we let P equal the proportion of potatoes with blemishes, and we haven't done P yet, so we'll get to that next chapter. Our null hypothesis is that the proportion of potatoes with blemishes is 0.08 or technically higher. So we'll just put P equals 0.08. The alternative, which is what the potato chip producer wants to find, he wants to see that the proportion of potatoes is less than 0.08. So, our type 1 error, we're going to reject the null when it's actually true. Again, the null is whether it's 0.08 or possibly higher. The producer concludes that the proportion is actually less than 0.08 when the actual P is greater. You're rejecting the null even though it's true. So your sample tells you you've gotten a proportion that tells you it's statistically significant that it's less than 0.08. The consequence, the producer accepts shipment with inferior potatoes. Other consequences, consumers may choose not to come back to the product after a bad bag of potatoes. So that is one consequence of the producer making a type 1 error, rejecting the null when it's actually true. Type 2 error, failed to reject the null when it's actually false. So the producer concludes that the proportion of blemishes is 0.08 when the actual proportion is within range where he should accept the shipment. Alright, so you're failing to reject the null. In other words, you possibly accept this when it's actually false. And then the alternative is true. The consequence, the producer rejects the shipment with acceptable potatoes that causes possible damage to the supplier relationship and to the production schedule. That might mean failure to meet the demand of consumers and distributors, which will cause a financial hit. So there are real-life consequences when errors are committed, but they do happen. Alright, our next example. You've created a new manufacturing method for producing widgets, which you claim will reduce the time necessary for assembling the parts. It currently takes 75 seconds to produce a widget. The retooling of the plant for this change is very expensive and will involve a lot of downtime. So, here are our hypotheses, and the last one you'll try to figure out on your own. Let mu equal the mean time to produce a widget. So, our null hypothesis is that it still takes 75 seconds. Because we want to produce them faster, our alternative is mu less than 75 seconds. So we want to show that our evidence tells us that the production time for each widget has actually decreased. Let's see what happens when we commit different errors. If you reject the null when it's true, in other words, you find that your data tells you that there has been a decrease in production time for a widget when there actually hasn't. You conclude that the new process reduces the time when it actually doesn't. So sometimes you're going to have to do some mental gymnastics, think about it, draw a little table, and figure out what the description is. The consequence, you end up spending lots of money retooling the plant when there will be no savings. Because you've concluded, yeah, let's retool the plant because we're producing widgets faster, when in actuality, you're not. So you lose money because you unnecessarily shut down the plant and you lose valuable production time. So a couple things could happen there, real-life consequences. You shut down the plant to retool the machines, when in actuality, there was no difference between your original method of production and your new method of production. If you have a type 2 error, in other words, you fail to reject the null when it's false, you determine that the new process does not reduce the time when it actually does. You fail to reject the null. You think that the new process has not improved the production time or decreased the production time. So you fail to reject the null, but in this case, the alternative is actually true. The consequence, you end up using the same old process when you created an approved process. You lose the opportunity to save time and money, and thus you have fewer widgets to sell. That should be saved, not same time. All right? So there are, again, real-life consequences to errors. In this case, even though you make a mistake where you don't retool the plant necessarily, you miss out on an opportunity. And in business, there are opportunity costs, which are lost chances. All right, it's response time. A city manager staff takes a random sample of 400 emergency call response times for life-threatening situations and found the mean response time X bar equals 6.48 minutes with a standard deviation sigma equals 2 minutes. The manager wants to know if the response time decreased from last year's mean of 6.7 minutes. The idea behind it is he wants to get it down, the response time down, to save more lives, and he's going to take measures if it's not reduced. So, see if you can construct these hypotheses yourselves. Pause the video and try to figure out the consequences and the descriptions of type 1 and type 2 errors. Alright, here are our hypotheses. Remember, we're trying to see if the response time has decreased. So our mu is the mean response time of the paramedics. The null, mu equals 6.7 minutes. There's been no change in the response time. The alternative is that the response time has gone down, so the mu is less than 6.7 minutes. Now let's see if we can recognize what the descriptions and consequences of type 1 and type 2 errors are. Type 1 error, we reject the null when it's true. The manager concludes that the response times have improved when they actually haven't. In other words, you're rejecting the null, you're accepting that the response times have improved, when in reality they haven't. The consequence? The manager will not authorize additional funding for improving response times, and lives might be lost due to the slowness of the response. So those are a couple of real-life consequences for a type 1 error. You're rejecting the null. You're saying that there actually has been improvement when there actually hasn't. Type 2 error, failing to reject the null when it's false. The manager concludes that the response times still need to be improved when they actually have improved. So, in other words, the manager thinks, oh, great, the response times haven't improved, when actually they have. So, the city may have to spend a considerable amount of money it didn't need to spend to improve response times because they were already at the response time target they needed to meet. So this might also cause some disgruntled paramedics among the troops because they'll be working hard and unhappy that they still need to get funded for more help because city manager doesn't think they're doing a good enough job. So a lot of this is just kind of doing the mental gymnastics, thinking things through, writing out the consequences if you need to in English, and then putting it together. Alright, so here's our summary. Remember, statistically significant does not mean practically important. Small differences from alpha to your p-value, they make a difference. The less the p, the larger the statistical significance. Smaller p-value means more significant. I just mentioned that. Faulty data collection produces bad conclusions. Remember, garbage in, garbage out. For type 1, type 2 error, if you reject the null when the null is true, you've committed a type 1 error. If you fail to reject the null when the null is actually false, you've committed a type 2 error. And remember to always give a description and consequences of each error. Remember, type 1 is considered a false positive. A type 2 is considered more like a false negative, if that helps you kind of conceptualize things. Alright, hopefully you stayed awake through this entire video. If you haven't, that's fine. I won't know anyway. So, you'll get problems to do in class on Tuesday or Wednesday, depending which period you have me. And if you have any questions, feel free to shoot me off an email or post a message on the Facebook page. Ciao.